Good afternoon, everyone. So something a little more fun today, keeping things kind of back to basics, and using Maple to talk about Hollywood math. So sometimes we kind of see physics or math get a little crazy in Hollywood, and so I'm going to go through some examples of what that might look like if we break it down into the basics. So to get started, one of my favorite movies, many of you may be familiar with Up. So the main character, Carl, decides to go on a worldwide adventure and with his house. So technicians at Pixar estimated that it would take 23.5 million party balloons to lift a 1,800 square foot house like Carl's. So in the film, the animators actually used 20,622 balloons for the liftoff sequence, and then later on used 10,000 just because animating that many balloons consistently would be quite complicated. But how many balloons in real life would the physics actually take to lift a house of that size? So let's calculate that in Maple. So air weighs about 0.078. Bigger? You guys can't see this?
Plus one. Magnifying glass. Thank you.
Magnifying. Better? The back?
Wouldn't hurt to do it again.
Okay.
You just can't see. What's in
So air weighs about 0.078 pounds per cubic foot, and helium weighs about 0.011 pounds per cubic foot. The helium balloon experiences a buoyant upward force that's equal to the air it displaces minus its own weight. And this might be knowledge to some of you, all of you, maybe none of you, and you're looking at me like, okay, cool, that's fine. The reason I'm going through this is for any of you that are instructors, professors, these are examples that may be interesting to your students to engage them. So for any of you looking at me, okay, cool, this is great. Why are we doing this? This is for students. So we can put these equations in Maple. We go through. I'm not going to delve too far into the math. As I said, it's the basics. But going through this, and I've already gone through the evaluations, but basically comes out to be that 1 cubic foot of helium can lift 0.67 pounds. So if you're buying party balloons and you're looking to do some at-home experiments, there we go. Now, when I was doing some research into kind of putting this together, if anyone reads Wired, they already put together a whole article on this, so it kind of made it a little easier. But they estimated, and they looked into, I think, professional movers, the guys that go in, the steel beams, pick up houses and move them somewhere else. But they said most houses weigh between 80 and 160,000 pounds. And they also assumed, for the purposes of these calculations, that Carl's house in the movie, based on looking at different images, different angles, that Carl's house weighed 100,000 pounds. Now again, if we plug that into Maple, we run the calculation, we end up with 1.49 times 10 to the 6 foot cubed. Now, if we were to use quite large spherical balloons, let's say 3 foot, if we look at the movie and they're quite big, we can calculate, again using these same equations, that they each have a volume of 14.1 cubic feet. If I keep going, because I'm just spewing numbers, we end up with 105 105,575 point, blah, 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 blah. But one of the fun things you can kind of put into Maple, so I said between 80,000, and this is probably looking real small at this point. If I can make this bigger, my slider bar. Can I? It doesn't get bigger, nope.
Just like a plot.
It's one thing to put on the list. But we can add components. So sure, we can do the math on if we're at 100,000 pounds, but if we're at 80,000 pounds, if we're at 160,000 pounds. So we can kind of go back and forth in between and make that calculation nice and easy from what we had before.
Remind me, what did they predict the number was supposed to be?
105,576 balloons to lift the house.
Yeah,
What did
engineers-
Pixar use? 20,622. And then they used 10,000 throughout the rest of the movie, just to keep things simple.
Oh, they asked me 20, party.
Oh,
Those are
what they
party
actually
balloons.
used, party balloons, small balloons.
Yeah.
Yeah, they said 23.5 million. But then they actually used 20,000. Sorry. But yeah, smaller balloons, so probably half the size.
Times to the third power.
What?
To the third cube.
Yeah, right, so that's what I'm trying to take the cube root.
So my next movie, it's quite, if anyone, depending on a different crowd, but in Mean Girls there's kind of this famous scene. There's a math club where they have these mathletes, where they have this math competition, and it kind of gets to the end. There's this tiebreaker where both teams choose a single competitor to compete in sudden death. And there's this equation responding that the limit of the equation as x approaches 0 does not exist. So calculating this in Maple, we can calculate the limit easily with our context panel. Limit from both sides. Whoop. Limit point to 0. Limit is undefined. Why is that the case? So if we look at it from both sides, we can break down limit from the left side is negative infinity. And again, the limit from 0 from the left is positive infinity, hence undefined. So it's just a neat way to be able to explain to students why something is the case. Of being able to break down those problems a little simpler than, oh, it's undefined. So it often comes up that superheroes are magical, godlike even in the case of Thor. We have his hammer, Mjolnir. We often see them kind of breaking the laws of physics. So according to Stanley, Thor flies with something he calls hammer propulsion. What this breaks down to is simply conservation of momentum, physics principle that we're probably all pretty familiar with. So breaking this down, it's a principle: any object with mass gains momentum as it moves, simply the product of mass and velocity. So if we look at this as a problem in terms of Thor and his hammer. So the way this works is Thor has his very, very heavy hammer, and in Marvel lore, the massive Mjolnir, his hammer, is sometimes assumed to be infinite. So the purposes of this calculation, we're going to attach a very, very large number to it. So in lore, it was once stated that Mjolnir is made of a neutron star matter, and that implied by legend, it would weigh the equivalent of 300 billion elephants. So assuming that a single elephant, I looked this up on Wikipedia, it's an African elephant weighing 2,268 kilograms, multiplied by 300 billion, we end up with 6.8 times 10 to the 14 kilograms. We'll also assume a couple of variables. So velocity of the hammer, I'm going to assume that it's 45 meters per second, and this is the speed at a major league pitcher can throw. The reason I'm assuming it to be that is that although Thor is not a major league baseball pitcher, he is a superhero. He's very strong. I'm going to assume he can throw his hammer very, very quickly. The weight of Thor, according to Marvel Wiki, is 291 kilograms. For anyone looking at that in pounds, I believe it's, probably do the conversion if able, but it's around 600 and something pounds. He's big. He's a big guy. He's pretty heavy. I would not want to get into a fight with Thor. But anyway, putting all of that into our M1 times V1 equation and solving out for our V2 and isolating that. Solve, isolate for our V2. We end up with basically 45. If we go back and we look, nothing's changed. We've ended up, and these cancel out. Thanks, Maple. But they cancel out that the velocity of the hammer has not changed. So why is that so? Go ahead.
Can you explain the way I'm looking at it? Maybe it's my being a nerd here.
Yep.
The left side, is that the initial state or the final state? Is he catching his hammer or is he throwing his hammer?
So he is. He swings his hammer and he basically spins it so fast,
Yes. And then
releases it, catches it, basically propelling himself to fly.
Okay. So, all right. If that's the case, and
Uh-huh.
he throws it at 45.
Mm-hmm.
So you wouldn't put his hammer weight in the second line on the right hand side. You just leave the 291 times V2. Because, right?
Well,
It's gonna
no.
go that way.
Wonder if he's gonna grab it and fly with it,
Mhm.
you gotta count his weight too.
Right. The point.
And that's the thing. So it
Oh,
doesn't
so
matter
he's-
what
so
he
he-
weighs, cause the
And
hammer
that's-
weighs so much.
That's the point that I'm making, is that the hammer weighs so much that,
Oh, he holds on to it as he.
yes.
Oh, I didn't understand that.
Okay.
Yeah. You're right. Then actually, it's impossible for him to go.
Right. We're in Hollywood. In theory, he would have no arm left, it would be ripped out of his socket, and Thor would no longer exist. Except he's a superhero and a god and all of the rest.
I understand.
But in putting this through,
Right.
the math checks out that we're still moving at 45 meters a second, and the hammer's so big that the hammer and Thor still move at the same speed. everyone's following. I feel like I've lost everyone. But the hammer's so heavy, the small addition to its mass won't make a difference, which I thought was kind of a cool thing. So the Fast and the Furious. I don't know which, I guess this one's the 6th one. I'm not quite sure which one we're on at this point.
The one that beats Rainbow.
But in the 6th movie, the final scene features a very, very, very long runway. The scene lasts over 10 minutes. I believe it ends up being about a 15-minute long scene. So there's been lots of debate over how long would this runway have to have been if it was actually a real-life runway and we weren't all living in Hollywood. So the scene has multiple phases. The plane landing, slowing down so people can board the plane as it's moving, speeding up to take off, landing again because of too much weight, finally crashing at the end, all within the scene and the very long runway. So the plane itself during the scene fluctuates between 100 miles and 170 miles per hour. But it's known that on average, because a lot of people have analyzed the scene, that it traveled about 115 miles per hour. And we're saying that the scene lasts around 15 minutes. So Maple, we can do this calculation. It's a pretty simple speed of travel divided by distance over time. So substituting on those values, 115 times 15 minutes, we ended up with 28.75 miles. So according to Wikipedia, the longest runway in the world is at Camdo Airport in China and is actually 3.42 miles. So not even close to our very, very long runway in this movie. So my last example is the movie 21, in which Ben Campbell solves his professor's problem about a game show involving the Monty Hall problem. It's a very famous problem. The host of the game show, Let's Make a Deal. So here's how it works. You're in a room with 3 doors, and the host, Monty Hall, asks you to choose one of the 3 doors and receive the prize behind that door. So behind 2 doors are goats, and behind the 3rd door is a brand new car, which I assume most of us would want the car over a goat. So before your door is opened, Monty opens one of the doors, revealing a goat. He asks you if you want to change your selection to the 3rd and the last remaining door. So, do you switch or not? Can I get a poll of hands? Would you switch? Can I get a poll of hands who wouldn't switch? Can I ask why?
Because I think in reading Monty Hall's mind, I think he is evil, and he does not want me to win.
Okay.
So I've clearly picked the door with a car in it.
Okay.
And I will win 100% of the time.
Okay.
Probably these other people think Monty Hall actually wants me to win.
Fair enough. Fair enough. They're laughing at you.
I deserve it. How about it?
So the correct answer is that you do want to switch based on probability, not based on that Monty Hall may or may not be evil. But you'll only ever have the expected 1/3 chance of winning the car. However, once the host opens one of the doors, revealing the goats, you obviously do not improve your chance of winning to better than 1/3 of the chance of your original choice. However, if you do not switch doors, there's a 2/3 chance you will win the car. So we actually have one of our math apps is the Monty Hall problem. So if you ever go exploring into Maple, if you take a look at the math apps, I do have it open already. But if you go into, I don't know if it's in Help or from the front page, is it in Tools? Things have the math apps right here. But it's always open when you open Maple. There's a math app section, and you get to the Monty Hall problem. So, would anyone like to pick a door?
One. I have my hand up. Oh, I didn't see you. Just had to yell.
I guess I should pick the door first, right? I would be Monty Hall, so
No, Monty Hall doesn't pick the door.
I thought he picked the door
You
first.
don't have to let Chris pick the door.
Isn't that how it works? He picks the door and then
Martin shows us a go.
oh, he sits to the door too. Okay, okay.
Pick the door.
Is he picking a door?
Two.
Selected. So then you pick if you want to switch or not. So do you want to?
I'm gonna switch. And 3.
So it didn't work that time.
He's evil. He's evil.
Sorry.
No, in that case, he's not evil because you have a 1/3 chance of picking the right one from the beginning.
Mm-hmm. Would anyone else like to give it a shot? Anybody?
2.
Thank you. 2? We're going 2 again? Okay. Let me reset. And 2. Okay.
Let's switch.
Switch. This one. Nope. I did not rig the game.
I programmed it myself.
But one thing we can.
Do a reset first.
Yeah.
I did do a reset.
This happens.
Just runs evil.
Yes. So that's what I'm going to do now. So what I'm going to do is we can see that we can do an automated. So right now I have it set for play 20 rounds. And as it's playing, we can see wins versus losses. Right now I have it set to always switch the doors. So it's hit that 57% wins. So I'm going to keep it at 20 and always keep the door. I'm sorry, my friend, but if you always keep the door, probability says, uh-oh. You will see, so that stayed at 46. If we go back to always switch the doors and put it up to 100, we should get pretty close. So 61%. 61%. So it's a little low, but it's a neat little app to play around with. Anyway, that's my talk. So if anyone has any questions, let's open the floor.
What was that limit problem at the beginning?
I can go back to it.
I just wanted to write that.
Mm-hmm.
I think I know what it was, but I just wanted to write it down.
Mm-hmm. Awesome.
Yeah. Okay.
Actually, I like the Thor's hammer one because I'm about to do conservation momentum. So
Oh, nice. Nice. Yeah, and there's lots of things to be able to do that. I work in Maple Sim a lot more, so being able to show kind of more, I'm not as much in Maple, but being able to show more the simulation of it and that kind of thing, especially being able to use like the pendulums and that is neat as well. Mm-hmm. Have any more questions? Okay, well, thank you, everybody.